Welcome back to our course on memory device technology for AI/ML computing. Let's try to recall what we had covered in our previous session. In the previous session, we did a deep dive on the von Neumann architecture. Let's quickly recap that. The key insights that we gained from the von Neumann architecture was that spatially it consists of separate memory and logic elements which are connected by the data bus. The kind of operation that happens in von Neumann systems is essentially deterministic or run by a predetermined program. It is sequential and clocked, and most of the implementation is in the digital domain. We also discussed that it is quite antithetical to how human brain computing works, and therefore when we try to force fit AI/ML algorithms on von Neumann systems, there is a huge amount of power consumption and latency owing to the bus which connects logic and memory because of very frequent data transfers in the data driven computing regime. Okay, so next, as we know, today we will do a deep dive into the memory element. Let me bring out my pointer. So today we will begin our journey at looking very carefully at the memory element. If you want to look very deeply at the logic element, I would suggest that you can do a course in microarchitecture. But this course, as you know, is focused on a deep dive into the memory element. So we ask the question. Structurally, the memory element is very simple. Functionally, also quite simple. It has addressable memory cells or memory locations through which you can to which you can do read and write operations. But is the implementation so simple? And as I had hinted in my introductory video, that the implementation is not quite simple. And the example that I had given that time is that of a startup growing up into a large corporation. As you know, startups generally begin with a very few number of people. They have 2 or 3 founders. They do most of the work. But as the operation of the startup starts growing, there are more number of people that are included at various levels in the organization. And as you can see, from a full-fledged organization, it will have the CEO right at the top. Then you will have upper and middle management, then engineers and factory floor workers, and etc. So hierarchy is very, very important, although the young generation seems to not really like this word. But hierarchical systems have become very, very important throughout human history to deal with complex systems with a lot of moving parts. And just to emphasize upon that fact, today we will see a very simple example which all of us can relate to. So today we are going to look at the problem of personal finance. So remember, when you were a small kid in school and you had to go to school, wanted to buy some food in the canteen for snacks, at that time your parents used to give you just some cash and they used to say, use it wisely and return whatever is left. So for a school student, just dealing with cash is enough. But now you have come to do your undergraduate and graduate studies. Most of you have moved away from home. So no longer your parents can come every day and give you cash. So they opened a savings bank account for you, right? And the instruction to you was very clear. Only withdraw in cash what you need for immediate needs. Small amount for immediate needs. Rest of that, let it be safely placed in a savings bank account. Correct? Hopefully you will graduate, get very good jobs. You will find very high paying jobs. And at that time, the general tendency of a lot of the youngsters is to spend a lot of money buying not very useful things or partying. So parents go ahead and say, no, this is not the right way to go about life, or they also become very aware of their financial situation, and you should stash away some money in form of fixed deposits, right? So now what has happened is, in addition to savings bank and cash, you need another savings instrument in forms of fixed deposit where you will keep away money for future needs. And of course, you grow older, you have a family, you will have a spouse, you have elderly parents to take care of. They will have their own needs in form of insurance. You will also try to invest in other kinds of instruments like mutual funds, stocks, etc. and your personal finances kind of grow. So am I giving you advice on how to invest your money? No. The point I'm trying to make is very simple. In as something as simple as I won't call personal finance simple, but as mundane, which everybody has to deal with. As your complexity grows, the need for newer instruments also becomes very evident, right? What a school kid can manage with personal finance, a family man cannot. Also, each of these new instruments have a place in the chain of hierarchy. They perform specific roles. For example, cash is for immediate needs, whereas fixed deposit is for long-term needs, right? And all of this is arranged in a so-called hierarchical setup. One thing that you should notice, and you will see in most hierarchical setups, right at the top, if you see the amount of cash that you generally deal with is a very tiny fraction of what is generally put in a savings bank account, which is for 6 months use, which is a tiny again fraction of what you put in your fixed deposits or mutual funds. So going down in the hierarchy, the amount of money that is being stashed away keeps growing, right? And therefore we say that although this is a good way to explain different needs and different hierarchy, maybe there is a better diagram to elucidate that. But before we go into that, let us look at how the evolution of memory hierarchy has come. So now I hope it is very, very clear. What is the need for hierarchy? Need for hierarchy arises because when systems become complex, you need different instruments to perform different roles in and work cogently or coherently. Does that make sense? So let us look at how memory systems have evolved in their hierarchy. This will be the theme for this course, for this particular session, and also the next session. Today we will look at the evolution of memory hierarchy from a very systems perspective. What were the growing needs, computational needs of the system, and how the evolution in the memory hierarchy supported these needs. Does that make sense? Okay. So I have not, as you see in the x-axis, I have put time. I have not put specific dates or specific years because a lot of people were working parallelly on these systems, right? So we can just generally talk about trends. So when Intel was in one direction, probably Qualcomm was in another direction. So this is a very fungible thing, but overall needs moved together. So let's begin right at the time where in early 1960s or late 1960s, where for the first time you started using solid state devices for decision making. Earliest example is when you sent your first manned mission to the moon. So at that time NASA used a very simple system as indicated over here. It just had a CPU and it had a main memory, and the objective was to do control systems for the different moving parts in your whatever spacecraft, correct? And it was to do autonomously. So just the CPU, which was taking inputs from the surroundings and making decisions, and the main memory, which was storing these inputs in real time. And also the job of main memory, as we saw previously, was also to store the code, the sequence of events that the CPU is supposed to follow, right? This was good enough for a basic control system. However, people soon realized that computational systems have now become powerful enough to not only do real-time systems but also do computation. So when you do computation, you take a bunch of data, just like our example of computer-aided design, and there is a final result which has to be also stored, right? And this final result or the result of the simulation, I want to see after some time. I want to analyze after some time. So as you know, in main memory, you will not have enough space to do that. So you need another form of element way down in the memory hierarchy, which you can use for storage. As you can understand, the meaning from storage, the meaning of storage is very simple. It is to store data or archive data which we have processed but we don't need immediately. And this is where the terminology between storage and memory becomes very evident. So memory, the notion is you want to put in the data which is for your immediate needs of computation, and therefore it has to be very close to the CPU. Whereas the storage, the idea is to have more capacity so that you can archive stuff which you may need for future purposes. Does that make sense? So in that case, from correlating from our previous example, we can say that the main memory is more like the savings bank account and the main storage is more like a fixed deposit. Does that make sense? Yes. So next, what people figured out is this hierarchy was working very well until they realized that because of advances in the transistor technology, the CPU operation become much faster as compared to the main memory. So just imagine that the CPU is able to crunch out data very quickly, but the main memory is not. So there will be a big bottleneck at this particular interface between the CPU and the main memory, right? This is because CPU is becoming faster, main memory is not really being able to keep pace. And that is why people realize that you need to have a different kind of memory which can act as a buffer in this bottleneck. And this is the invention of the so-called cache memory. And it's quite remarkable. It sounds quite similar to our previous example. Here CACHE is similar to the previous example of CASH. The objective is very similar. In cash, we use for personal finances for immediate needs, to go to the grocery store, buy some tea, buy some sweets or whatever. And here also for cash, you store memory, you store data which is absolutely relevant for the CPU's current operational cycles. Does that make sense? In addition to that, people also saw that the amount of data that you are now generating is filling up your main storage, right? Because computing systems have become faster and better, you are able to do much more computation. That's why you are able to generate more analysis, more data. This is filling up your main storage. And therefore, there was another element which was added to the memory hierarchy, which is called secondary storage. The objective is very simple. Main storage is for things that you will need once in a while. The secondary storage is more for archival purposes, right? This is how we also manage a lot of our emails. You archive things which you think you will need once in a blue moon, okay, so that it doesn't clog up your inbox. After that, we saw that there is a significant change in even the cache architecture. Earlier, the cache architecture used to exist outside the CPU subsystem. People realize that however well you design this system, again the bottleneck becomes between this very fast CPU and the cache. Although the technology is the same, they existed in different dies or different chips. So the idea was, can we have one level of cache which is embedded inside the CPU, and this will have the fastest access times, right? And that is why even cache architecture started evolving to what we have for most systems at the present day. In the present day system, this looks like the most recent memory hierarchy which is implemented in most of your laptops, if not mobile phones, where you have your CPU, you have 3 levels of cache. In high performance systems, you even have 4 levels of cache. You have L1, L2 and L3 cache. We will look in details of what is the meaning of these L1, L2 and L3 caches. For the time being, you can understand there are 3 levels of cache. L1 being closest to the CPU, L3 being further away from the CPU. And this entire subsystem is what interacts with your main memory, and the main memory is what interacts with your main storage and secondary storage, right? So this is what is the evolved memory hierarchy, and I could tell you, probably convince you, that all of these complications have come because of growing needs, growing complexity. So is what we have done presently, have we frozen in time? Not really. The requirements for the future are even more intense. And what we are currently saying is, just like previously there was a big bottleneck between the CPU and main memory, as we will discuss in the next class, there also exists now a significant bottleneck between the main memory and the main storage. And people are now inventing new kinds of memories which are called storage class memories, which will bridge the gap between main memory and storage. Okay, so I hope I was being able to convey to you how the requirements for computation changed, the complexity changed, and therefore this led to the evolution of the memory hierarchy. Okay, while we see that this is a very nice way to look at memory hierarchy, there are from a very top perspective, now we will dive into the details by looking at each and every element, what is the latency, what is the cost, and what is the device technology. But I hope it is clear why the memory hierarchy evolved in the way that it did. And to be really able to appreciate the details, the technical details of evolution in memory hierarchy and how the memory hierarchy is at the present day and how it is supposed to evolve, we need to look at some very important technical terms. So we will spend the next 5 to 10 minutes closely looking at these technical terms, defining them, and this will be very, very important for the rest of the course. So these classifications, which are often interchangeably used, and there is a lot of confusion even in the community, we should clarify, our concept should be clear, then the understanding of information will become very, very clear. Okay, so let us begin. What are these important classifications that we need to understand to appreciate memory hierarchy? The first is between latency and capacity. So first, what is latency? As you can imagine, latency is how much time does the CPU require to access data from a memory element in the memory hierarchy. So this access time can be measured in seconds. Generally it is in nanoseconds, microseconds, milliseconds, or it can be measured in CPU clock cycles. Okay, so it can be number of seconds or how many clock cycles does the CPU have to wait before it can access the memory, the data stored in a particular memory. Okay, what does this depend on? It depends on the memory elements technology, right? What is the technology with which the memory element has been meant or the storage element has been meant? That is obvious, but what is less obvious is the input-output interface. Let me go back to the previous slide. Previous slide, we could just, in a very cartoonish way, we have represented this input-output interface with just a bidirectional arrow. As you can understand, it is not so simple. Actual implementation is very difficult, and the quality and the design of this input-output decides how good the latency is. I'll give you a very quick example, and of course when we go to DRAM we will go in details. The example is between single data rate and dual data rate input-output interface between the CPU and the main memory. In SDR, single data rate, data is transferred only on the rising edge of the clock cycle. However, in dual data rate, because of improvements in technology, you can now access data in the rising and falling edge. Therefore, your throughput becomes double, your latency becomes half, right? So input-output interface and interface technology is also very vital. Next is capacity. What do you mean by capacity? Capacity is how much of memory, generally in GBs, can you store in that particular memory element. And this, of course, is directly tied to bit density. This is a technical term we will keep using. What is the meaning of bit density? Bit density means how many bits can you store per unit area. So it is generally as bit per micrometer square, bit per millimeter square, etc. Right? As you can understand, higher the bit density, more is the capacity of the particular memory or storage element. Now, ideally you would expect, or ideally you would want some memory or storage element with very low latency and very high bit density. Unfortunately, nature and engineering is full of trade-offs. That is generally very, very difficult to achieve, and they are directly linked. Most of the times, not sometimes, most of the times, and most generally, if something has very low latency, generally the capacity is also very low. What are the details for that? We will look very soon, but it is good to have this broader perspective of things, that there are no free lunches. Generally, I'll repeat, generally with lower latency, you also have lower capacity. Details of why and what we will go into very soon when we look at individual elements. Okay. The second thing that we should look at is on-chip versus off-chip memory. So when we say on or off, with which chip are we referencing to? The answer is the CPU, right? So the question when we ask is on-chip versus off-chip memory, is it in the same die or same chip as the CPU or not? This is the question we try to ask and answer. Why is this very important? It is very clear. If a cache is within the chip of the CPU, of course, latency will be much smaller than a cache which is outside the chip of the CPU. Why? Because this input-output interface will add to the latency. Does that make sense? Okay. Generally, not always, generally, whenever you embed a technology within that chip, it is, or whenever you embed a memory element within the chip, it is generally made from the same technological node or same technology node or same fabrication processes as the transistors used for the CPU technology or CPU computation as well. Okay. So again, on-chip versus off-chip becomes a very important and vital distinction because of the same trade-off we just discussed. It is capacity versus latency. On-chip will have lower latency, but of course a little smaller capacity also. Moment you take things off-chip, you are increasing the latency, but the opportunity to have more capacity also increases. I hope that makes sense. Here I have put a disruptive technology called heterogeneous integration. I'm just giving the term. Don't get scared of the term. We will go into details when we look at DRAM cells. Heterogeneous integration is the methodology of taking two technologies which are built taking two dies which are made with completely separate technologies and embedding them in the same subsystem. And this could prove to be a game changer when it comes to playing with this trade-off of capacity and latency. The attempt is to get the best of both worlds, right? So this we will discuss more in detail. I just wanted to kind of sprinkle this information at you. Next, let's move to the third important distinction or classification, which is important to understand the memory hierarchy. The third distinction is memory versus storage. In memory, as we discussed in the last slide, whatever is the data that is absolutely essential for the CPU's immediate needs are to be stored. And therefore, the expectation from memory elements is that it will have very low latency. Of course, it will suffer a little bit in capacity and it will be higher in the hierarchy. Why higher in the hierarchy? Because latency needs to be lower. It needs to be closer to the CPU, just like we saw in the previous slide. In storage, the idea is slightly different. In storage, you want to store data which you would probably need after some time. And therefore, in storage, although you can afford a little higher latency, you also want very high capacity, right? This is very important. And to just give you a distinction between memory and storage, a following example may be very vital. The example is that of running CAD simulations in this kind of memory hierarchy. So what do you think? Just pause for a while and try to think when you are trying to run a iterative method or a simulation which uses the iterative method in this kind of hierarchy, what will be stored in the memory and what will be stored in the storage. So as you may have guessed, the immediate needs of the CPU, which are the code and the constants of the equations of your differential equations or your difference equations, and the data from the few iterations before will be stored in memory, whereas storage will contain the final output. I hope that is you are able to make sense. Another example, because I want to really emphasize that the difference between memory and storage. If you see in local parlance, generally we use these terms interchangeably. I want to emphasize today that you should not use them interchangeably in this technology course, right? Memory simply means immediate use, low capacity. Storage is high capacity, long-term use. Simple example again would be from our human being computing. Suppose you book a Uber. What stays in your memory is the number plate of the Uber car, which you can forget as soon as you finish your ride. But what should stay in your storage is, or long-term memory, should be the number plate of your own car, because you will keep using it. I hope with this contextual difference you are able to see what is the difference between memory and storage. Okay, so let's move on to the next important classification: volatile versus non-volatile. So what is the difference between volatile memory and non-volatile memory? The idea is, can you retain data or can you hold on to data when the power supply to the memory element is switched off? This is what decides whether something is volatile or non-volatile. Correct? So you will have when you switch off the power supply, but you are still able to retain the data which was stored in that memory or storage element, it is called non-volatile. Whereas if it forgets, then it is known as volatile. So as you can see from previous definitions, because memory elements in the hierarchy store immediate information, there is not always a need to remember them. So in general, memory elements are volatile, whereas storage elements are non-volatile. Here there is a important technical distinction. When we talk about storage or ability to hold on to data or non-volatility, what does it mean? For how long should be the device element able to hold on to data? And a simple definition which comes from industry standards is 10 years. If you store a bit into a memory element, a storage element, and it is able to retain it for 10 years, then only probably you can call it a non-volatile storage element. I have an open question now for you guys, which we will cover when we go to NAND flash, but I want you to think about this. Suppose you are a company who has just invented a very good storage element. Of course, you cannot wait for 10 years to test it and see whether the data stays. You have to release in the market within 1 year, otherwise your technology will become obsolete. So the question is, how do these companies test that a storage element is non-volatile for 10 years? Open question. Please Google, please think about it. We will cover it when we come to when we discuss about storage elements, especially NAND flash. Here also, what we will discuss in the next session, storage class memories. We can bridge the gap between the technical definitions of memory and storage by having a new class of memory elements called storage class memories, which will have very low latency but also high capacity, which will be non-volatile but also be very quick, and therefore storage class memories could be the future of having non-volatile memory. Okay, so what I want to give you a sense of, that these definitions, although have specific meanings, they are not frozen in time. They are continuously evolving. The next thing that we should look at and which confuses a lot of students is random access versus sequential access. Random versus sequential access. So what is random access? Suppose you have a bit array with addressable locations from 1 to 100, just as an example. In random access systems, the time required to access bit 1 or address location 1 or address location 20 or address location 40 or 100 is more or less the same. This is because different addressable locations or bits stored in different addressable locations can be randomly accessed at will. This is not the case with sequential access. In sequential access, you cannot access bit number 20 without going through the sequence 1, 2, 3, 4 till 19. This is absolutely important. This distinction should be very clear. What is the difference between random access and sequential access? Let's try to understand random access and sequential access by a very important example. It is by how we listen to music versus how our parents' generation used to listen to music. Today, if I want to listen to a A.R. Rahman album, for example, I download the album, I have all the songs in front of me, and I can directly go and click on the 5th song on my phone and I can listen to the music. But this was not available to our parents. They used to listen to music in tape recorders. In tape recorders, there is no way to directly go and select the 5th song. You have to plug in the tape, you have to fast forward from the first song, second song. You don't need to play it, but you need to fast forward from first song, second song, third song, fourth song, then pause and then only be able to play the 5th song, right? So this example gives you a very clear distinction of what is random access in a mobile phone versus sequential access in a tape recorder. Does that make sense? Of course, random access, you will have very low latency. You will be able to access the data bit at will very quickly. Whereas in sequential access, the focus is not really on latency. It is on higher capacity. In sequential access times will be much slower. So now anybody would try to think, then what is the point of having sequential access? Why can't we have random access all the time? And this is why I want you guys to start thinking like engineers. Please understand, in engineering, there are no free lunches. Everything is a trade-off. And as you will see when we study SRAM cells, to facilitate random access, the amount of peripheral circuitry that is required is very huge. The amount of circuitry required to implement random access becomes significantly large part of the area and the cost of running the circuit. Does that make sense? And you will see when we go to NAND flash, which is essentially sequential access, that the amount of peripheral circuitry becomes much smaller. In fact, in SRAM, it can sometimes happen that the peripheral circuitry can be equal to the memory array itself. That means the amount of cost or time or the space that is required to store the bit is equal to accessing the bit also. Reminds me of this food delivery app where nowadays to order some food, it takes significant amount of convenience fees. Sometimes it could be similar to the price of the thing that I am of the food that I am ordering, right? And this is the price that you pay for convenience, for access, for low latency. Okay, so never think that only one thing is good. Okay, each has a particular role and they have their costs and they also have their associated benefits. The final thing that we want to look at, and we will look in detail, is static versus dynamic random access memory. So what is the meaning of static versus dynamic? As you remember, in random access memories, especially memories, the moment you switch off the power supply, the data is generally lost. That is what we saw, that memories are generally volatile. But even within the volatile subclass, even when the power supply is on, you will see there are two kinds of memories: static memories and dynamic memories. In static memories, once you store the bit, there is no need to keep refreshing the bit. It is permanently stored till you switch off the power supply. However, in dynamic random access memories, as you will see, the bit is stored in a capacitive element, and as you know, capacitors leak charge. So since capacitors will leak charge, you will see that you need to continuously refresh the data to retain it. Okay. So with this important classification, 6 classifications, I hope you will be able to understand the concepts that we will discuss further in the memory hierarchy. Please pause the video at this time. Go through each and every of these 6 pairs. Make sure that you understand. Try to recall these concepts. If not, please go back to our discussion and review it again. The last thing we want to discuss for today's session is introducing you to the memory hierarchy pyramid. Okay, so as you can see, you have a pyramidal structure in the memory hierarchy. At the top of the pyramid, what you can call the CEO, is the logic or CPU element. The logic or the CPU element which will request for stored memory or stored data will be right at the top of the pyramid. Here you will see, arranged in a pyramidal fashion, is different elements. You can see the L1, L2 and L3. The dollar sign is generally used for caches. So we will abbreviate sometime caches with a dollar sign, generally used in technical parlance, followed by main memory. Then you will see that there is a huge gap, and we will discuss what this gap is. To understand what this gap is, we need to understand what is the meaning of the X and Y axis in this particular pyramidal structure, followed by primary storage and secondary and tertiary storage. So now we would like to address one of the most important questions in this particular course. Why do we have the arrangement of the memory hierarchy in form of a pyramid? What is the meaning of having things in pyramid? As we will see and have discussed, it is nothing but the trade-off between latency and capacity based on where the element is placed in the memory hierarchy. For example, as you can see, as you go further down in the memory hierarchy, the idea is more about storage. You need to store the elements, and therefore you need larger and larger capacity. As you can see, while L1, L2 and L3 caches have memories in the orders of KBs and MBs, the main memories, you buy these phones and laptops, you see they are typically in the range of 4 to 64, very high performance of 128 GB, whereas primary storage, your SSD drives have roughly 1 TB, 1 to 10 TB of data, and your secondary storages, which are generally used in the cloud, for hundreds of TBs. So as you go further down in the memory hierarchy, because the amount of information that you want to store increases, you have to have elements which have higher and higher capacity or higher and higher bit density. Okay, this is the meaning of the pyramid. That means that the base of the triangle at every element is indicative of what is the bit density, right? Smaller the base of the triangle, smaller is the bit density. Higher the base of the triangle, size of the triangle, area of the element, it means that higher is the capacity. The other thing that we see is, of course, in L1, L2 and L3 caches in main memory, you store the most recent data. That is why they are placed closest to the CPU subsystem, and therefore they should have very low latency. So this is the trade-off which I wanted to indicate through a straight triangle and an inverted triangle. When you compromise on latency, you get higher capacity. Okay, so while the latency from the caches are in the orders of nanoseconds, in main memory is in the order of hundreds of nanoseconds. In primary storage, it can be as high as microseconds, tens to hundreds of microseconds. And we will not discuss more about tertiary storage or secondary storage, because they are not solid state memories, they are magnetic tapes, and therefore it is very clear what this gap that I have indicated in orange color indicate. It's the huge gap between main memory and primary storage. There is probably 2 orders of magnitude gap between the access times in main memory and primary storage. Okay, so with this, let us conclude today's session. Very brief recap of what we did today. First, we saw how evolving computational systems led to the evolving of the memory hierarchy. Second, we looked at 6 important definitions and classifications which are important for us to understand the pyramid, or why the pyramid is in memory hierarchies arranged the way it is, and why different elements will serve separate roles in the memory hierarchy pyramid. And finally, we got the first flavor and first introduction into the pyramidal structure of the memory hierarchy with trade-offs between capacity and latency. I hope this was a clear session. Let's meet in the next session where we will relook at the memory hierarchy from another perspective, which is memory device technology. Thank you.